experiment. Now you would think that if we fire these little electrons, more or less we should get the same result. Those electrons that go through the right slit land on the right in that band. Those that go through the left land in that band on the left side. But the thing is, if you do this experiment, this is not what happens. Instead, if you actually do this experiment, what you find is data that looks like this. Not just two bands aligned with the two openings. Instead, you get a whole series of bands. This is the heart of a revolution. And the key comes from another area of science called waves, right? If you are by a pond and you have two pebbles and you throw one pebble into the pond, you know what will happen. Pebble hits the water and it sends out these concentric ripples that spread outward. If you throw the other pebble in, you know what will happen. The exact same thing. Concentric ripples will be sent outwards. But if you are a careful observer and you throw both of these pebbles in and you look at what happens when the waves crisscross, you'll find something interesting. There are locations where the peak of both of the waves combine to make the water a little bit higher. There are other locations where the trough of each wave cross to make the depth of the water a little lower. But there are other locations where the peak of one wave crosses the trough of another, canceling each other out. At those locations, the water is not moving at all. The waves have interfered and canceled each other out. Imagine you throw in these pebbles, one on the right side, we throw in another one on the left, and where the waves are crisscrossing, there are locations where the waves are canceling each other out, and you can begin to see those coming into view here, the dark areas. Exactly the same kind of data that emerged in the little experiment where I was firing electrons at the two openings. So if you go back to this, the double slit experiment, the idea is now think of the electron as a wave. Like a water wave, it can crisscross on its way to the back screen. Locations where the wave cancels each other out, the dark regions are locations where you will find very few particles. Bright regions are where you will find the electron many times. So this is the core of the new idea. It's telling us that the world consists of waves of probabilities. You know, if scientists hadn't developed quantum theory, you could still imagine that very creative, smart, industrious engineers and thinkers of all sorts would still have learned how to manipulate the world on microscopic scales. They might not understand really the fundamental underpinnings, but through spectacularly inventive trial and error, you can envision that they would have developed much of the technology that we enjoy in everyday life. Cell phones and computers and all sorts of objects which rely on integrated circuits that we understand well because we have grasped the quantum laws. But what we'd be missing in a real vital way is the deep theoretical underpinnings of everything we see in the world around us. And that would be a huge loss.
Einstein and Planck may have opened the door, but it took another generation of physicists to dive deeper into the quantum world.
The uncertainty principle of Heisenberg was really a sharp turning point in the historical development of quantum mechanics.
Quantum mechanics revolutionized physics, but not without controversy. Find out who wins, who loses, and why reality might be stranger than you ever thought possible.